Alright, let's go over the midway practice worksheet review paper. Starting on question 1. What is the enthalpy change delta H in kilojoules for the following reaction? And it gives you a reaction, which I'm going to circle in blue. This is going to be our main equation that we work off of. And we have two other equations, sub-equations as I like to call them, in the red brackets. We're going to use the red bracket equations to eventually come up with the final equation we're going to make it into the blue equation, and we're going to calculate the delta H based on that. All right. We have 2Al. We're going to write it all out. We're targeting 1, the blue, 2Al, solid, plus Fe2O3, solid, and this is going to become 2Fe, solid, plus Al2O3, solid. And we're given the red equations like these right here, red equations 2 and 3. And so we look at the main equation and we see that the Al is where it's supposed to be, to the left of the arrow. And we know that the 3 over 2 oxygen cancels out because it's not existing. It's not existent on the blue circled equation. Then we know that Al2O3 is on the right-hand side of the equation, right here. And we can take a look at the third equation now because we know that we're not going to change the second equation. So I'm just going to bring it down below. 2Als plus 3 over 2 oxygen gas is going to become Al2O3 in solid form. Delta H for this is going to be negative 1676 kilojoules. All right, let's take a look at number 3. Number 3 is going to have a change because we know that the 2Fe has to be on the right-hand side of the base equation, but this is on the left. Same for the Fe2O3. If we switch it around, then it's going to be where we need it to be. So when we switch it around, I'll write it in black for clear. We're going to have Fe2O3 solid. That decomposes into 2Fe solid and 3 over 2 oxygen gas. And delta H value, since we flip the equation, we're going to flip the sign, and it's going to be 822.1 kilojoules. All right, so now we can take a look at our equation, and we can cancel stuff out. So let's take a look at this equation right here, this one right here, and we're going to look at it and cancel off. So we have 2Al, we can check that off. We have an Fe2O3 on this side, and we have an Fe2O3 on this side. Check that off. We have a 2Fe on the right-hand side. Check it off. And we have a Al2O3 on the right-hand side as well. We're going to check that off. So the only thing that cancels in this is the 3 over 2 oxygens. That's on the both sides. So the both on the reactant and product side. So we can go ahead and write our final equation for period. And then we have 2Al, which is right here, solid, plus Fe2O3 solid, which is right here, and then the arrow separates it, and then we have 2Fe solid here, and Al2O3 solid. Al2O3 solid. And we know the delta H is just going to be the sum of this, sum slash add, and when we add those two numbers together, we're going to get negative 853.9 kilojoules. And because the energy released is going to be a negative, it is going to be exothermic. All right, let's try number 2. What is the enthalpy change for the formation of hydrazine N2H4 liquid from its elements? And we have an equation. All right, let's circle that in blue. Use the following reactions and enthalpy changes. So these are the sub-equations that we're going to work with. So first rule, always write the base equation that we're targeting down. Nitrogen gas plus 2H2 gas, hydrogen gas, becomes N2H4 in the liquid form. All right, So now we have to take a look at our second and third equations, which are right here in red. Okay, so the first equation has N2H4 on the right side. Now our base equation has it on our left side. Our base equation has it on the right side, so we need to switch our equations. So we're going to do that right now. We're going to flip the equation. So it's going to be N2 and 2H2 on the left and this on the right. So N2 gas, nitrogen gas, plus 2H2O, and that is a liquid. It's going to be N2H4 in the liquid form and oxygen gas in the gas form. And our delta H, since we flipped our equation, is going to also flip, and it's going to be positive 622.2 kilojoules. Number 3, we can take a look at number 3, and surprisingly, we have everything we need on the left-hand side on the left-hand side, and the right-hand side on the right-hand side. Or this one actually cancels because it's not on any of the equations or any of the compounds on our equation, so we can ignore that for now. The only problem here is that we have a 2H2 on the base, and we only have a 1H2 here. So what we have to do is we have to multiply the third equation by a factor of 2. So when we multiply, it's going to be 2H2, and we multiply it across every single thing. 1/2 times 2 is going to be 1/2. No, sorry, 1/2 times 2 is going to be 1. So plus regular O2. You can put a 1 in front. Well, let's put a 1 in front. O2 gas. And then it's going to be 2H2O liquid form. Delta H changes also because we multiplied it by 2. We have to multiply our delta H value by 2. When we do that, we're going to get negative 571.6 kilojoules. All right, now we can start canceling because we have all of our equations organized. We have an N2 on this side and N2 on this side, so that is a check. We have an H2O here, but there's no H2O here, so we have to look to cancel it. We have an H2 on here. The left and right side, the left side and right side, they're going to cancel, so this we can ignore. All right, the O2, we have one O2 here and one O2 here. They're on the opposite sides of the equation, so like the water, we're going to cancel it out. And all we're left with is N2, 2H2, and N2H4, and that is our final equation. 4, and then we're going to add N2 gas plus 2H2 gas, and then our arrow is going to separate, and we have these covered, so we're looking to add and become N2H4 at liquid, and that matches our base starting equation exactly. Now all we can do, all we have to do is get this and add them up. Negative 571.6 kilojoules plus 622.2 kilojoules is going to give us a delta H change in enthalpy value of 50.6 kilojoules. And because it's a positive kilojoule value, it is going to be endothermic. Heat is entering the equation heat is entering the reaction. All right, let's try number 3. Like all carbonates, barium carbonate, BaCO3, can be decomposed to the barium metal. You have to remember that this is talking about barium. So it's going to be barium metal oxide, which is BaO, and carbon dioxide, which we know is CO2. If the heat of the reaction, delta H value, is 1216.3 kilojoules per mole, how many kilojoules of heat energy are required to decompose 10 grams of barium carbonate, so BaCO3? And answer if this is an endothermic or exothermic process. All right, so first we want to do is write our equation. Barium carbonate can be decomposed. So we have barium carbonate, BaCO3, is going to decompose into barium oxide and carbon dioxide, CO2. And we know that's balanced because barium 1 here and then carbon here, and we have 3 oxygens here. Matches the equation on both sides. Delta H value, it says, is 1216.3 kilojoules per mole. All right. And with this information, we have to figure out the change in enthalpy change in enthalpy of the we have to figure out change of enthalpy if the barium carbonate BaCO3 10 grams decomposes. All right, so we're looking for the delta H of F when 10 grams of barium carbonate decomposes. All right, we have to set this up using dimensional analysis. So change in enthalpy is going to be, we start with 10 grams of barium carbonate, BaCO3. Put that over 1. And to cancel the grams off, we have to use molar mass. The molar mass of barium carbonate is 197.34 grams. And then per 1 mole barium carbonate, BaCO3. And for every 1 mole of barium carbonate, we have 1 mole of reaction. We can know that 1 mole of the barium carbonate is, the bottom number is 1 because there's an invisible number 1 in front of the BaCO3. And for every 1 mole of reaction, we have 1216.3 kilojoules. And that is from this right here. That is a conversion factor that we are going to use. And it wanted our answer in kilojoules. So we're going to keep it as kilojoules because everything gram cancels, moles of barium carbonate cancels, and moles of reaction cancels. And we're left with kilojoules. So multiply everything on the top, click enter, and divide by everything on the bottom, and it'll give you 61.63 kilojoules. And that is your final answer. And you know that is endothermic because, yep, that is right. The number in front is a positive, there's no negative, so it is endothermic. All right. Let's try number 4. Nitroglycerin is a powerful explosive given 4 different gases when detonated. So when nitroglycerin, we're going to label it as Ng, blows, it's going to give 3 moles of nitrogen gas, 1/2 mole of oxygen gas, 6 moles of carbon dioxide, and 5 moles of water vapor. Given that the heat of the reaction, delta H, is going to be negative 3,426 kilojoules per mole, calculate the energy liberated, which means freed or exited, when 1 kilogram, we need that in grams, 1 kilogram is 1,000 grams of nitroglycerin, Ng, is detonated. And tell us if it's exothermic or endothermic. All right. All we have to do to solve this question is we're going to set up dimensional analysis. Same process as question 3. Delta H of nitroglycerin is going to be, we're starting out with 1,000 grams of nitroglycerin. We're going to label it as Ng because that chemical formula is very, very long to write. Start with this, and to cancel grams, we have to use the molar mass. The molar mass of nitroglycerin is going to be 454.22 grams per 1 mole of Ng. And for every 2 moles of Ng, we have to look on the equation for that part. 2 moles of Ng, we have 1 mole of reaction because we are only reacting once. 1 mole of reaction. And we have 1 mole on reaction, 1 mole reaction on the bottom to cancel out. And then we need to use our delta H value, which is negative 3,426 kilojoules. That is a conversion factor that we use to solve this question. Now everything on the everything cancels and we're left with kilojoules. So all you have to do is multiply across the top and divide by everything on the bottom, and that should theoretically give you negative 3,771.3 kilojoules. All right. And this we know is exothermic because, yep, the negative in front determines that the energy released or energy is released as heat, and that is negative and 3,771.3 kilojoules of energy. Let's try number 5. Calculate the enthalpy change for the following reaction and indicate whether the reaction is endothermic or exothermic. All right, so we're given an equation, and we have to use this chart at the bottom. Yep, this chart right here. We have to use this chart right here to determine our numbers. And this is going to be important because I have to write this all down. So we have carbon monoxide, we have carbon dioxide, and we have oxygen gas. But we have to note that oxygen gas is going to have zero value of delta H, change in enthalpy, because it is an element. It cannot have a positive, or it cannot have a number for a delta F because it's a singular element. And so we can set this up using the equation delta F. Delta HF is going to be sigma, that's the sum of the moles, times the moles of the change in enthalpy of the product side, product, minus the same thing for the reactant side. And the easy way to remember this equation is that delta H, similar to delta T, is going to be final minus initial. So this is going to be delta H. Delta H is like similar to delta T. So it's final minus initial. All right. So you have to look at the final. The final is the product side. So we're going to put an equal there, and we know that there is a 2 in front, so we have 2 moles, 2 times the value of the delta H value of CO2 is going to be negative 393.5, or 393.5, and then we have minus our 2 value here, 2 times, and the delta H value of CO is negative 110.5, plus 2, or 1 times 0, because oxygen has a 0 value for delta H. Then when we calculate this, this is going to be negative 787 minus 2 times negative 110.5, which is going to be negative 221. And all we got to do is make this plus plus, because 2 negatives equals a positive. So essentially what you're doing is negative 787 plus 221. And that will give you your final answer of negative 566 kilojoules. So your change in enthalpy is going to be this. And this is exothermic because there is a negative in front. And that is your final answer. All right, last question. Calculate the enthalpy change for the following reaction and indicate whether the reaction is endothermic or exothermic. So we can already tell that it's the same equation. Same solving process and same equation that we're going to use, that we used for the previous question. All right, so we know the CO value is going to be negative 110.5. We know the Fe2 value from this chart on the bottom. Let's make it green highlighter. So Fe2O3 negative 822.1, and we know that Fe is going to have a value of 0 because it's an element. And CO2 has a value of negative 393.5 kilojoules. All right, so same way we set it up as the previous one, delta H of F equals the sum of the moles of the enthalpy of the products minus the same thing of the reactants. All right, so then our answer is going to be set up to solve like this. 3 times the value of CO2 is negative 393.5 plus 2 times, and the delta H value of Fe is going to be 0 because it's an element, minus 3 times the value of CO, negative 110.5, plus 1 times the value of Fe2O3 is negative 822.1, and all we got to do is solve. So this is going to, this part, negative 393.5 times 3, is going to equal negative 1,180.5, and it is going to be minus, and minus 110.5 times 3 plus negative 100, or negative 822.1 is going to give you negative 1,153.6 kilojoules Two negatives make a positive, so you're doing negative 1180.5 plus 1153.6. Your answer is going, delta H value is going to be negative 26.9 kilojoules. And we know that is exothermic because there is a negative. Heat is released in this reaction as well. And that is it